So, we looked at an analytical method for synthesis of a function generator. So, typically something like this. So, you want to generate a 4 bar with a uniform x scale and a y scale, and you take the input angles to be proportional to those. So, say this is with 3 precision points. So, this would. So, from the equations for the Chebyshev spacing, these are the design criteria you get. Okay. So, you get phi 2 1, what we normally refer to as phi 2 1, phi 3 1, this is psi 2 1, psi 3 1. Okay. So, we want to design a function generator for this. I just wanted to show you, I will have to figure out how to do MATLAB online here, but so I just ran it offline to show you some options. So, here in the first case, so I have taken phi 1 equal to 0, psi 1 equal to 0, okay, and I end up with the link lengths like this. So, this is R 1, R 2, R 3, R 4. You can see they are very disproportionate, 17 times. And you can also see if I do, this is the smallest link S L, S plus L is equal to P plus Q. So, you get the change point, you get a Grashof neutral linkage because you chose phi 1 equal to 0, psi 1 equal to 0, the first precision point, right, you get a change point there. So, this is probably not a desirable solution. So, I change my conditions a bit and accordingly the scale will change. So, I would use this equation. So, here I keep phi 1, I change phi 1 to 45 degrees, I retain psi 1 as 0. Okay. Then I ran my code again, okay, and I get a much better linkage for it. Okay. So, this is my, this would be the first position A 1, B 1. You can see this is phi 1 equal to 45, this is psi 1 equal to 0, this is O A, O B, this would be A 2, B 2, A 3, B 3. So, this would be the example of using Freudenstein's equation using a programming language like MATLAB to do your synthesis. I could have done this graphically also, but it is harder to do, to cycle through multiple solutions. Also, in the graphical case, if you noticed, once we specified one link length, especially for 3 position synthesis, I did not really have control over the initial orientation of the output link because of the method that I used. It has more to do with, when I used inversion, I found that I could not really specify, I had to find the intersection of the 2 perpendicular bisectors, which is a point which is not necessarily on what I want psi 1 to be. Okay. So, that is a solution I get, but here I am able to specify. So, the geometric methods may have limitations in terms of, because of the parameters I have to specify for the construction, I may be limited in some way. In this case, I am able to specify both the precision points. There in most cases I only worked with the 2 displacements, angular displacements, and I specified only one of the angles, initial angles. Okay. So, that is something to keep in mind. So, we will now move on to block synthesis, which we started yesterday. So, I have, we take a general So, if I take these vectors say r 1, r 2, r 3 and r 4, okay, and say this is my r 1 is my fixed link. So, the first equation that I had was r 1 plus r 2 plus r 3 my loop closure plus r 4 equal to 0, and I wrote this in complex form to get r 1 e power I theta 1 plus r 2 e power I theta 2 equal to 0. I differentiated this with respect to t, because now I want to perhaps specify conditions on the derivatives of the linkage at a particular position. I wanted to have a certain input and output angular velocity or certain input and angular acceleration. So, I get differentiating. So, we saw that I will get I omega 1, obviously the first term will be 0, r 1 does not change. So, I get I omega 2 r 2 e power I theta 2 plus I omega 3 r 3 e power I theta 3 omega 4 r 4 e power I theta 4 equal to 0. Okay. I of course goes away. So, I can write this as omega 2 r 2 plus omega 3 r 3 plus omega 4 r 4 equal to 0, right, in vector form. So, this is one equation, this is the other equation, and then I differentiate it again with respect to time. I get I into alpha 2 plus I omega 2 square e r 2 plus I into alpha 2 plus I omega alpha 3 omega 4 square r 4 equal to 0. Again I can knock off the i's. Okay. So, now I have a set of 3 equations like this. I have r 2 in these 3 unknowns. I want to synthesize the linkage. So, r 2 r 3 the links are my unknowns, this equal to 0, omega 2 r 2 and then alpha 2 plus I omega 2 square r 2, sorry, this is not equal to 0, this is minus r 1 I omega 3 square r 3 plus alpha 4 plus I omega power 4 r 4 equal to 0. So, if I specify, if I choose r 1, okay, I get a set of linear equations in R2, R3 and R4. Okay. They have complex coefficients, but nevertheless it is a set of linear equations in R2, R3 and R4. So, I can choose some R1 again, and in case of angular quantities I can scale, should not be a problem. I should be able to get a linkage to satisfy my design conditions. Okay. So, now if I can write this, if I write the solution in determinant form, R2 will be equal to, let me go back to minus R1 1 1, okay, R1 0 0 1 omega 3 alpha 3 plus I omega 3 square omega 4 alpha 4 plus I omega 4 square. That will be the numerator, and the denominator will be common for all of them. It will just be, so if I take denominator determinant D will be the determinant of 1 omega 2 alpha 2 plus j omega 2, sorry, 1 omega 3 alpha 3 plus I omega 3 square 1 omega 4 this will be my determinant. Okay. This will be D, and D is also going to be a complex number because there are complex coefficients in the determinant. If I expand this, I get minus R1 into omega 3 into alpha 4 plus I omega 4 square minus omega 4 into alpha 3 plus I omega 3 square by D. Okay. And similarly, I will get for the other 2 R2. Now, my R1 is a free choice. So, one way I can simplify my calculations is to say that R1 is proportional to D. So, say I say let R1 equal to minus D. D is a complex number, right. So, that way I eliminate this and I have only this to evaluate, becomes a lot easier to evaluate that. Okay. Similarly, I will have for R3 and R4. I will let you write that out because I am going to have you do an assignment on programming this. Okay. And then you can verify with the example that I will show you. So, if I choose, so then it just becomes a matter of if I want my R1 to be horizontal, okay, which is what I started off with, I would basically have to rotate it because any complex number I can write in terms of, so if I have a complex number R, it is some R e power I theta, where theta is the angle it makes with the positive x axis, right, the magnitude and the angle in polar coordinates, right. So, this would be just R angle theta in polar coordinates. I choose some R1 to match. So, if I choose it to match the denominator, then my calculations become simple. So, I can find an R2, R3, R4 in this manner, and then of course, once I find the linkage, we will do the example which will show you what it looks like, what you will get when you solve it this way, and then how you would get the configuration that you desire. So, this is a problem. You design a 4 bar linkage in one of its positions you want it to satisfy the following specifications for omega 1, omega 2, omega 3, alpha 1, alpha 2, alpha 3. Okay. So, I would program, if I use Bloch's method, then these are my initial conditions and I end up with a linkage. This is my solution from MATLAB and I get these vectors. So, this is R 1, R 2, R 3, R 4. These are my link lengths, which are basically the modulus of that those vectors. Okay. So, I get these link lengths. Now, let me see what my linkage looks like. So, if this is my complex plane, R 1 is minus 2.2, let us say I take the scale to be 1 equals 100 here, because it is that times. So, I have minus 2.2 plus 3.08, that is the largest link. So, it would be somewhere here, that would be my R 1. R 2 0.6 plus 0.12. So, I have, it will be in the first quadrant, much smaller. So, let us say this is R 2. R 3 is along the negative y axis and my R 4 is in the third quadrant again. So, let us say this is R 4. R 4 is smaller than R 3. Okay. So, now I have to form the loop with this. Okay. So, this is my R 1, which is the fixed link. Okay. So, my loop becomes, this is R 2. So, I move it, that would be my R 2. My R 3 comes straight down. Okay. So, this is my R 3, because I have to satisfy my loop closure equation, R 1 plus R 2 plus R 3, then okay, this should be R 4, they should be parallel to this, but yeah. So, this is R 4. So, this is my linkage. Okay, the book uses a different notation, sorry, alpha 2, alpha 3, alpha 4. The book uses 1 for the input link and uses 4 for the fixed link. So, this becomes your linkage. Now, if I want to have this with R 1 along the real axis, then essentially I have to rotate this whole linkage by clockwise by this angle. All the vectors have to be rotated by the same angle, otherwise you can pretty much use it in any orientation in the plane and it will still have the same behavior. Okay. So, this is Bloch's method of synthesis. So, both Freudenstein's equation and Bloch's method I will have you code in MATLAB, so that given a set of conditions you will be able to synthesize a linkage for that. Otherwise, we will move on to the analytical synthesis of a driver diode. I will do the synthesis of a non-quick return, meaning time ratio equal to 1. Grashof 4 bar to drive a rocker through a specified angle. So, practically usually your rocker movement should not exceed about 120 degrees. Okay. If you want more than that, you typically go to like a 6 bar. It is difficult to, because your transmission angles become very low. So, your force transmission is poor. So, practically you want to keep the rocker excursion, the rocker range to be less than 120 degrees or so. Okay. So, let us start off with what we are given. I have start somewhere here. B2 and say I have some initial angle, not, although it looks 90, I probably do not want it to look 90. So, let us make this B1. This is some initial angle theta 4. Okay. So, I am given R4. So, I know B1 and B2. This B1, this link may actually be the input to another 4 bar, like the double rocker that you did for the function generation in the last example. Okay. The one with the Freudenstein example, this one, this is a double rocker, it is a Grashof double rocker, but it is not a crank rocker. So, you may want to attach a driver diode to it, in which case the output of this driver diode is basically the input to that 4 bar, as we have seen several examples before, and say this angle is beta. Okay. So, now my task is to find the other 3 links R1, R2 and R3, such that this linkage gives a time ratio of 1, and I want to synthesize it analytically. Geometrically we know, and we will kind of use that in the synthesis in developing the equations, but if you had to do this geometrically, you would join B1, B2, extend it, pick some point on that line, then take half of B1, B2 to be your crank, and then you have your synthesis done, and then you just check for Grashof. Okay. So, here now we will do. So, here this is the vector R O B. So, I can find, this is given, I know the location of O B in the plane. So, I can find R B1 is R O B plus R4 e power I theta 4. R B2 equals R O B plus R4 e to the power I of theta 4 plus beta. Okay. So, I can find the location of B1, I find the location of B2. I need to locate my, for a non-quick return linkage, I need to locate my O2 somewhere, OA somewhere on that line. So, if I designate this vector, see I know B2, I know B1, RB2, RB1. So, I know this vector, and let me call it M. Okay. M is nothing but this is RB2, this is RB1. So, RB1 plus M is RB2. So, RB2 minus RB1 is M. Okay. So, M is RB2 minus RB1, just vector addition, right. So, now I can say my ROA, OA will be located somewhere here on this line, which would be at a location which is, so I can write this as ROA will be equal to RB1 or RB2 plus some constant times M somewhere along that line, and I can choose that constant typically around 2 to 3 times. Okay. So, K, typical values of K if you want to get a crank rocker somewhere between 2 and 3 is a reasonable choice. Again, it will depend on the problem, but this is just a guideline. It could also be on the other side. So, it could be plus or minus K. Okay. It could, I could very well locate. Now, I know that R2, what would be the magnitude of that? It would be half the magnitude of M. Same thing, same, you know, it is exactly as we did the geometrical synthesis. So, R2 is half of this thing. So, this is half of, in terms of beta, I can write it as half R4 sine of beta by 2. Perpendicular bisector if I draw beta by 2. So, this is R4, no wait, yeah, is it just R4 sine beta by 2? This is beta by 2, yeah, it is just R4 sine beta by 2, not half of that. Half of this whole thing R4 sine beta by 2. So, now do I have everything I need? I have found OA, okay. I know my crank length. The only thing left is R of A, okay. So, if my OA is somewhere here, this is R2, okay, and that would be A1. So, RA1 will be, again if I find the unit vector along that line, it will just be, yeah, R of this minus half along that line. Minus R2 along. So, if I have m by mod m, that would be the unit vector along. So, now I have all the parameters I need for the design. Again, you would program this, and you are also going to develop the equations for time ratio not equal to 1, following a similar procedure, because you already know how to do it graphically. It is a matter of translating that into equations for doing this. Okay. So, this is the analytical synthesis for a driver diode. So, it could be for a crank rocker, standalone crank rocker, or for a driver diode for another 4 bar. So, output of this becomes the input for the other 4 bar for continuous input, and your R1 will essentially be mod of ROB minus ROA, and R3 will be mod of then you check for Grashof, very important. If you are designing a crank rocker and you do not check for Grashof, so this method is given in Norton's book, this analytical synthesis for the driver diode. Okay. Most of the other material I have been taking from the Dennewitt and Hartenberg-Dennewitt book, and most of the figures are also there. I stopped putting in every slide because it is freely available, and that's sort of like the textbook that I am following for this course. For most of this course we will be using that book. Okay. All right. So, again with these methods that we have seen so far, we are only looking at it being at certain positions, assembling the linkage at certain positions. Okay. So, it is quite important that you are able to simulate the linkage, okay, over its entire range in order to be able to determine whether it is reaching those positions without encountering a branch change or toggle positions. Okay. So, because of that, let me just do the position analysis for those of you who have not done the position analysis using the complex number technique. Since I have some time today, I am just going to do that very quickly. It is similar to what we did with Freudenstein's equation, but let me just go through it so that you can program that as well. When you do the design, you do the analysis of you do the position analysis as well. Okay. Just for the sake of completeness, I will cover that. Okay. So, we measure the angles with respect to the x axis. So, I have this would be theta 1, you would measure it at the root of the vector theta 4, theta 3 and theta 2. So, my loop closure equation for the way I have taken these is R 2 plus R 3 is equal to R 1 plus R 4. In complex form, R 1 e power I theta 1 plus R 4 e power I theta 4. For the sake of simplicity, I can always choose my x y in a certain way. So, let me choose it such that theta 1 equal to 0. Okay. Now, the 4 bar linkage, what I am trying to do here is position analysis. What does that mean? I want to determine for a given input, how many inputs do I need to give a 4 bar in order to get a predetermined output. So, okay, when you are doing analysis, okay, this is the difference between what we have done a lot of is synthesis. Synthesis is when you try to determine the link lengths. Now, what you are doing is you know the link lengths, you are given the linkage, you want to see whether it behaves the way you want it to behave. That is analysis. So, yes, in the case of analysis, link lengths are known. What else would you know if you want to? So, the 4 bar linkage has mobility equal to 1. which means if I give it one input, then everything else becomes determined. Okay. Typically, theta 2 will be my input. So, what I have to now find is for every theta 2, I want to find out what are theta 3 and theta 4, because if I know that, the link lengths are all constant, they do not change for the 4 bar. So, I can basically construct the 4 bar in every position. Now, it is very easy to do this graphically. You can construct the 4 bar very easily when you do it graphically, because you just need the link lengths. Then from this point you set it at this angle theta 2, an arc with length r 3, another arc with length r 4, and you are done, if you know the configuration. And in fact, in MATLAB you can construct it that way. You do not have to actually go through all this, you do not have to program these equations. MATLAB I think has this circ command. Anybody aware of MATLAB has this circ command, I think, intersection of two circles. So, you can use that intersection of two arcs to actually find that easily. So, you can construct it in MATLAB by doing that as well. Okay. But here we will just go through the analytical set of equations. So, we want to find theta 3 and theta 4 if theta 2 is the input given. This is a vector equation. So, I can only solve for two unknowns, which will be theta 3 and theta 4. But again, theta 3 and theta 4 are in transcendental form in this equation. So, it is a little bit more tedious to solve it. So, the first thing I will try to do is to eliminate. So, I write this into real and imaginary parts and say I want to eliminate theta 3, like we did when we derived it for Freudenstein's equation. There our purpose was different. We knew the theta 2 theta 4 combinations for which we were finding the link lengths. Now, we know the link lengths, we want to find if it behaves the way we want it to. So, I will just take r 3 cos theta 3 separating into real and imaginary parts. I have taken theta 1 as 0. So, I have r 1 plus r 4 cos theta 4 minus r 2 cos theta 2. Then I have r 3 sin theta 3 equal to r 4 sin theta 4 minus r 2 sin theta 2. Okay. Now, if I square and add, my only unknown will be theta 4 in these two equations, right. I square and add these equations and I get r 3 square equal to r 1 square plus r 4 cos theta 4 cos theta 2 plus sin theta 2. Okay. So, I get r 1 square, r 4 square cos square I will get plus sin square. So, r 4 square, similarly r 2 square cos square plus r 2 square minus 2 r 4 r 2 cos theta 4 cos theta 2 cos theta 2, these two are gone, minus 2 r2 r4 sin theta 4 sin theta 2. Here I will not try to simplify these because theta 2 is known. Okay. So, I want everything in terms of theta 4. So, I will group them as r1 square plus r4 square plus r2 square, okay, plus some k1 a1 cos theta 4 plus b1 sin theta 4. This would also go with this one minus 2 r1 r2 cos theta 2. This would be, so this is a constant. So, this, so I can say this is equal to a1 cos theta 4 plus b1 sin theta 4 plus c. I do not even have to call it a cos theta 4 plus b sin theta 4 plus, I should take this also to the other side. Okay. Let me just put this as equal to 0, where my c would be r1 square plus r2 square plus r4 square minus r3 square minus 2 r1 r2 cos theta 2. All this is known. Theta 2 is my input, all the other angles. Sorry, I want you to, what's the, when you want to solve an equation like this, what's the most common substitution you do? Yeah, use the tan theta by 2 formula. Express both cos theta and sin theta in terms of tan theta by 2 and solve, you will get a quadratic equation.